welcome everybody to Lecture 8 of Advanced Inference and Graphical Models. And today we're going to talk about a couple of things that I think are fun. Today might be a fun lecture, and it's actually an important lecture because we're going to talk firstly about intersection graphs, which was the thing that we sort of briefly began at the end of the last lecture. And then lastly, we're going to talk about inference on junction trees. And so if there was a moral of today's lecture, the moral of today's lecture, which I'm going to give you at the beginning, is the following. So this is to be read poetically. Junction trees are, or I should say, a junction tree is the tree that all graphs can be transformed up into. Once we have such a tree, we have a variety of options of doing message passing that generalize the message passing on trees that we've already seen in the first couple of lectures of the class. And moreover, if we wanted to, once we've got a junction tree, we could actually reduce that back down to a one tree, but with higher cardinality variables. So in some sense, basically, all graphs are treated as like one trees via this process of maybe seemingly circuitous, but in fact not so circuitous, this process of going through a representation in terms of a triangulated graph and then a junction tree, I should say, of Maxcliques. Okay, so let's do a brief review and make sure that there are, resolve any questions, any lingering questions that you might have. Although I guess that since today the homework was due, probably everybody's sort of caught up and everything's relatively fresh in your mind. So there are three views of the running intersection property: the clique intersection or the cluster intersection property, the induced subtree property, or this order-based constraint on an ordering of the clusters. Each one of them we saw are equivalent, and we are calling them collectively as the running intersection property, which means we can use any one of these three views interchangeably. And a junction tree is a cluster tree that satisfies the running intersection property. A junction tree might or might not be one where the clusters are cliques or max cliques of the original graph. A junction tree could consist of all of the variables together in one giant clique, right, or one giant cluster, I should say. So that basically means that, in fact, we saw that a junction tree is a tree of cliques with respect to the original graph, if and only if the original graph is triangulated. So if the original graph is not triangulated, it's not possible to construct a junction tree of cliques or max cliques. Question?
Last time you said a junction tree also had the edge cover to it?
Yeah, a junction tree also has the edge cover property under something that there are no isolated vertices. So all vertices have to be at least connected to one other vertice. Okay. So yes, edge cover too. Maybe I should add that. Plus an edge cover. We saw that there was an equivalence of triangulated graphs, decomposable graphs, perfect elimination graphs, and the junction tree of cliques exists. And very, very soon, in fact, the first part of today's lecture, we're going to see that it's also equivalent to this notion called a subtree intersection graph. And then the inference, our goal is essentially to express the cliques as marginal, so that we actually ended up having a marginal distribution over all of the clusters, or over the cliques or the max cliques in the original graph. Okay, so that's where we're at. Any questions? Okay, so last time we talked about an intersection graph. So the basic idea of an intersection graph is the following. You start with the original graph, okay, and you have a set of vertices and a set of edges, which are right here. And then for each one of these vertices here, for each vertex in that set V, we have some set, U sub V. Okay? And U sub V basically is a subset of some underlying large ground set U. But the set that U sub V is a subset of is in some sense irrelevant, or not entirely irrelevant. It's not really necessarily directly related to the set of either original nodes or original edges. The idea is that the subset U sub V, which is this thing, is used as sort of a testing ground to decide whether or not there exists an edge between, say, U sub V and U sub U. So we say basically that it's an intersection graph if it's the case that there's an edge in the original graph only if the corresponding sets, U sub U and U sub V, are intersecting, meaning that the intersection is non-empty. Okay? So that means that there's some underlying set of objects, U. So U is like everything. We can call this a ground set. And there's a multi-set of subsets of U of the following form. So it's script U, which is U1, U2, up to UN. And there's n such subsets because where n, remember, n is equal to the size of the original graph, the original vertex set of the graph, G. So n is the number of original graph vertices. And we have that many subsets of U sub 1 through U sub n. Each one is a subset, and it's a multi-set. Basically, it means that we might actually have two sets, U sub I and U sub j, being identical. That's fine. Now, how does it essentially construct a graph? Well, basically, again, if there's an edge, so let's say here's the original graph. Let's say this is U, and this is V. And if this edge exists, then that must mean that U sub U intersect U sub V does not equal to the empty set. Now, in some sense, you might think this is a trivial definition. And if you thought that, then you would be correct. Because it actually turns out to be the case that every graph is an intersection graph. So we really haven't really done anything. And the way you can show this just very, very easily is basically there's no constraints on the set U. Right? U could be as big or as small or countably infinite or uncountably infinite. It doesn't matter. You can always make U to be rich enough such that any graph can be expressed. In fact, it could be the case that every U has that there's sort of essentially a set of distinct entries in U corresponding to every edge, and we're certain that the corresponding sets U sub U and U sub V have that element corresponding to the edge between U and V. It's very trivial. Now, it becomes less trivial when we start adding and looking at types of sets. Like, okay, well now we're saying, okay, well it's what is the type of sets that say U sub I might be? Okay, as opposed to just an arbitrary set. Then it becomes interesting. The first type of set that we're going to consider are intervals, where every U sub U or U sub V is just an interval on the number line, a real number line. So basically, every set is of the form AB. Okay. Now, any graph that can be constructed as an intersection graph of intervals, where the sets are intervals, is what's called an interval graph. And this is a class of graphs that's well known to graph theorists. And here's an example. So we have a set of intervals here, A, B, C, D, E. And remember, every set corresponds to a vertex in the original graph. So that means that this interval here corresponds to this vertex. This interval here corresponds to this vertex, and so on and so forth. This interval here corresponds to this vertex. And basically, we say that there's an edge between two vertices, let's say between A and B. Okay, this edge here exists if it's the case that A and B's intervals overlap, if there's an intersection of the intervals. And similarly, there's an edge between, say, E and C, because E and C overlap. And there's an edge between, I don't know, any one of these other ones, E and D, because E and D overlap. Okay, so basically intervals are the objects, are the set objects. Okay? Now, question for you, are all graphs interval graphs? We know that all graphs are intersection graphs, but are all graphs interval graphs? No, why not? Right, a cycle. Exactly. The fourth cycle is not an interval graph. The reason why is because if we consider, do I have a picture here? Yeah. So if we have a picture, let's say that A, B, C, and D. If A is connected to B and A is connected to C, whereas D is connected to B and D is connected to C, it must be the case that there are intervals. The intervals are such that A and D also overlap, or alternatively, that these guys overlap, right? Yep.
But the definition does not preclude the case that it should be minimal in the case that if there's no edge between A and D, there should not be overlap between.
It says that as long as the sets do not intersect, there's no edge. That's the definition. And intersecting of an interval means that they share a point in the real line, right? So like think of these guys here. Remember, these are the line intervals. The idea is that if you take any vertical line, so that must mean that A and B share an edge, A and E share an edge, and B and E shares an edge. And so if we had, like, let's say we did A, and then we did B, and then we did C. Okay, so this is trying to construct this 4 cycle, and then here's D. The only way to make C and B connect to D is this way. The only way to make C and A connect to here, which basically forces A and C to have an edge. So therefore, we can't do the 4 cycle. Interestingly enough, we can do the chorded 4 cycle. Question?
Yeah, in terms of your notation, what's the superset U in this example?
In this case, the superset U are the extremes. So it would basically be the real number between here and the real interval between here and here.
So it's just covering all possible U, V's, and U's.
Yeah, so it's like, it would be the union of all intervals, which I guess there's no requirement that there aren't gaps. So it might involve some gaps, right? That's a valid thing. So it would be the union of all connected intervals that union together, not including the gaps. That would be the set. That is a set, right? It's a set of real numbers. It's a countably infinite set of real numbers, but it's a set nonetheless, and it's perfectly well defined. Okay. So the way that you get U in general, going back to the original definition here, is U here. This is a little bit hard to draw because it's U is equal to the union of I in the interval 1 through n of U sub I. Okay? And if U sub I are intervals in the real line, then we just union them together. Okay? Good. It's clear? Okay. So all graphs are not interval graphs. But on the other hand, all interval graphs are triangulated. Why must it be the case? Because you take any cycle. I mean, it's a very simple idea here. We take any cycle, right? And so this involves edges along the cycle. And in order for this to involve intervals, there are going to be intervals that go, say, this way. But then to go back along the cycle, the intervals have to go this way. And so obviously there's going to be at least one chord. So all cycles are chorded. So all interval graphs are triangulated. Question: are all triangulated graphs interval graphs? Yes? No? YouTube audience? This is the Coursera aspect of this course. So test. If we were Coursera, we would like jump to a software avatar that would pop up and say, sanity check. Are all triangulated graph, sorry, it would say it much better than I just said it now. Are all triangulated graphs interval graphs? The answer is no. It's a little bit of a tricky question. So consider the elongated star graph, like this guy. It's kind of like a spider graph in some sense. So if it's the case that this, first of all, this is clearly a triangulated graph, right? It's a tree, in fact. If it's the case that this is a graph, and we've got this bit here, and we also have this bit here, right? It would have to be the case that there are some additional edges added to this. Because anyway, so if it was the case that this was an interval graph, then if E and A and B and A are connected, that means that E's interval and B's interval must both overlap with A. But then D must overlap with A and C must overlap with A. But that's not an edge, right? And this is not an edge. So it must mean that one of these edges exists, right? So therefore, that spider graph can't be an interval graph. But here's where it gets a little bit interesting and relevant to us. And this is a little bit subtle, so try to listen to this. Those of you who are on Facebook right now, or texting your best friend or girlfriend or boyfriend or whoever. So if it's the case that there's some underlying tree, because so we've got some tree. And now what we're doing is we're creating subsets, U sub v, as subtrees within the tree. And they're necessarily connected because it's a subtree. Okay, so in some sense, there's some underlying, in some sense, ground tree. And every subset of the ground tree is a subtree of the ground tree. And then we say that if we have u sub u and u sub v, which are subtrees of the ground tree, we say that intersection exists between those two sets, u sub u and u sub v, if it's the case that the two corresponding subtrees overlap. So we're only allowed to take subsets that correspond to a subtree. And then in some sense, you could think of intersection as being defined as normal, because you could think of u sub u and u sub v as being the vertices associated with the subtree corresponding to the subset, u sub u or u sub v. Now, pictures are worth 1,000 words. And this picture is probably my favorite picture in the entire course. So I was very proud of this picture. It took, actually, believe it or not, a very long time to do this picture. So let's zoom in on it a little bit. So here's the idea. And first of all, the underlying tree is, there's sort of like this ground tree, which is this whole thing here. Like that whole thing is the tree. Right? And I just highlighted it in purple, but I'm going to get rid of that because I just want to let you know that that whole thing is the tree. And that is sort of, if you zoom in here, you can see that there's sort of this black backbone. And so the black backbone is the tree. Okay? Then every subset of the tree corresponds to a subtree. So let's move in a little bit on the left. So for example, this guy here, T1, is a subtree. Right? T2 is a subtree. T4, this is supposed to look like brown. It probably doesn't look like brown. But T4 is a subtree, and then T3 is a subtree. And then this is a fairly large subtree. T5, T6 is a subtree, and so on and so forth. T10 is a little subtree which consists of the single node there. That's a valid subtree. T8 is a subtree. Okay, so that basically means that each one of these trees, subtrees, T1 up through T12, correspond to subtrees. So let me ask you, does T1 and T2 intersect? Yeah, because their nodes intersect. So the constraint really is in how you form the subsets. You can't take a subset consisting of, say, this bit and that bit. That's not a valid subset because it's not a tree. It's a forest, but it's not a tree. So it has to be a tree which is necessarily connected. Okay, everybody clear?
But do you have the requirement that you need to cover all the nodes?
You don't have to necessarily create all the nodes. What you have to do is make sure that all of the original vertices have a set associated with them. Okay. Anyway, so everybody get the idea that we are a subtree? Okay, good. So this subtree, this set of subtrees actually defines a graph. Why? Because intersection exists. So basically we have a set of nodes corresponding to every subtree in the original graph. So this is kind of like the original graph, or this is the intersection graph corresponding to this tree, or the subtree graph. And there's an intersection whenever there's a, or I should say there's an edge whenever there's in the graph between two nodes whenever the two corresponding subtrees intersect. So I think I've got an expansion of this. Yeah, so let's go over here. Let's look at this guy. So we can see to some extent that T1 and T2 intersect, right? So the corresponding nodes 1 and 2 have an edge. T1 and T4 intersect, so this has an edge. T2 and T3 intersect, so this has an edge. T2 and T4 intersect, so that has an edge. And so basically we look at all of these subtrees, the corresponding subtrees, see if they intersect. Like for example, take this funny one here, T10 and T8 intersect, right? So that means that 10 and 8 must have an edge down there. So remember, intersect is still the same definition of intersect because we're taking the vertices associated with each of the subtree and we're looking at intersection on those vertices. The constraint is that the subsets correspond to subtrees. Question?
So this graph that you started with when you're forming the subtrees, that's just like a regular tree?
You start with some tree,
Okay.
any tree. You take a bunch of subtrees. You take n subtrees, where n is the number of vertices in the graph that you're trying to construct. The tree is used to construct the graph. And basically, each subtree is associated with a vertex. And then the edges are defined based on whether or not the sets corresponding to the vertices of the subtrees intersect. Okay? So why does 7 and 5 have an edge here? Well, zoom in. And you can see that subtree T5 and subtree tree 7 intersect. Why? Because they share this common node in the tree. Okay. A subtree graph can have more than one underlying tree that defines it. Like we saw on the page that we just saw, that this subtree graph corresponds to this tree. But what about this tree? That's another tree. Let's look at that. Okay, so here's another tree. So here we have, just to zoom in on this tree a little bit, we have many, many additional single vertex subtrees, right? For example, now we have T1, T3, T12. Let's highlight T1, T3, T12, T6, T11, T8, T10, and T7. Those are all single vertex subtrees. That's perfectly okay. Those are valid subtrees. Then when we zoom in and look at the graph, we say, okay, well, we need to carve out all the nodes. So 1 is connected to 2. So the subtree T1 and T2 must share a vertex. Check. Pick any edge. Pick 5 and 9. Okay, so 5 is connected to 9. Why? Because, well, here's subtree T9 and here's subtree T5. They share a common node, which is this one. So that edge checks out. And then, basically, every single one of these things, all of these edges here, all correspond to this stuff down here. So let me ask you a question. What's the difference between the left and the right trees? I'm sorry?
Number of nodes?
Yes. Very good.
You collapse down extensions where there's no new intersections.
Yeah, that's right. You're sort of collapsing things down a little bit. What about answering this in terms of the cliques of the graph in the center?
Reduce Maxcliques to a single node.
Yeah, Maxcliques are like a single node. And what are the vertices on the right tree correspond to in the graph? Those correspond to Maxcliques, right? So the vertices on the right, in the right tree, correspond to Maxcliques in the graph. The vertices on the left correspond to not only Maxcliques but also cliques. So in some sense, the right corresponds to like a tree of Maxcliques. In fact, on the left we've got a junction tree of cliques and Maxcliques, and on the right we have just a junction tree of Maxcliques. These are in fact junction trees, but they're disguised. They're cleverly disguised inside of a tree. But it shows you very, very clearly that you're constructing. First of all, you might have noticed that the graph in the middle is triangulated, right? There's no chordless cycles, clearly. And so therefore, there can be a junction tree either of cliques or of Maxcliques, which consists of Maxcliques or cliques, which you now know from your homework. And what are the corresponding junction trees? Well, here they are. So we have an underlying graph. Here we have a junction tree of Maxcliques corresponding to this subtree. And so this is a subtree graph corresponding to this tree. It's the same graph corresponding to this subtree graph, but now we've got a different junction tree of cliques. And I have to tell you, by the way, I showed this picture to my 4-year-old son, and I was curious what he thought this picture was. And he immediately looked at it and said, "Oh, sheep." So there's these are called sheep graphs, or junction trees in this class are really sheep. You know, maybe this is kind of like, is this like a sheep? You know, if you could think of this as like a smile and two eyes, and there's 2 legs and a tail, it's a sheep. Anyway, children see the strangest things, or the most interesting things. Okay, but do you see? So what's interesting about this, moreover, is that we already have seen a theorem about this. In fact, first of all, these are the Maxcliques. Let's highlight them. And we've got the Maxcliques here, too. Like we've got this one. And they sort of pop up in strange places. 5, 7, which is here. 5, 6, 9, which is here. 9, 12, which is here. Or actually it pops up several places, lots of places. This one and 1, 2, 4. So let's zoom in on this junction tree. So those are the Maxcliques which I've circled. Does it destroy the running intersection property that I've got these extraneous Maxcliques here? No. That was like the theorem. In fact, we could have this endless tail of Maxcliques hanging off a Maxclique, and the running intersection property would still be there. Now, is there any particular practical reason to do this? Probably not, because I mean, if you've got a representation of 912 already, why would you need to hang off another representation of 912? Maybe there's some application in parallel computing somewhere, but I'm not aware of any existing reason for doing this. So while this is redundant, it doesn't seem to destroy, or in fact, it doesn't, in fact, destroy the running intersection property. What about these other ones here, like 1, 4 and 1, 2? That's more akin to what we've already saw. We're sort of hanging off cliques from a Maxclique, which are subsets of the clique. And here 2, 3, and 3 are subsets of 2, 3, 5, 2, 3, 4, 5. 4, 5 is a duplicate of this one, which sort of lives inside of 2, 3, 4, 5. 5, 9 can live with inside of its neighboring clique, 5, 6, 9, which sort of merges all these guys together. Similarly, this one and this one are sort of pendant. And similarly, here's 8 and 8, which hangs off of 8, 9, 10, 11. So that can be absorbed. So basically, all of those tan cliques are they might be Maxcliques, they might not be Maxcliques. In particular, like 912 is a Maxclique, but they can be absorbed into their neighbors. And what we end up getting is the junction tree on the right. So we have the following theorem, which says that a graph is triangulated if and only if it corresponds to a subtree graph from some underlying tree. And the underlying tree for which it corresponds to a subtree graph corresponds to a junction tree for that graph. And the proof of this is in some sense obvious now, because we have these 3 perspectives of the running intersection property, one of which is the induced subtree property. The induced subtree property is exactly this subtree graph property, right? Because every vertex in the original graph, take like, for example, this vertex here, T5, must correspond to an induced subtree, which corresponds to this induced subtree there. And just by definition, every vertex in the original graph, 8 or whatever, you pick a vertex in the graph, which is the center graph, and you're going to get a subtree either on the left or on the right. Okay? And what it is an induced subtree of is essentially a junction tree, but either a junction tree of Maxcliques or a junction tree of cliques, which includes the Maxcliques. Okay, so all interval graphs are clearly subtree graphs. And why is that case? Why is that true? Because essentially the intervals are chains. Right? There's nothing hard to show about that. The question is, are all subtree interval graphs interval graphs? Sorry, are all subtree intersection graphs interval graphs? We've already actually, believe it or not, answered that question. And you're right, the answer is no. Because we saw, for example, that spider graph. So that's clearly a subtree graph. It's a triangulated graph, but it's not an interval graph. The reason why we like them is because they capture the tree-like nature of triangulated graphs. And so in some sense, you can think of a triangulated graph as a tree. There really is just a tree. And we already talked before about the idea of a hypertree. It really is, in some sense, a hypertree, where the cliques correspond to hyperedges. And in the junction tree, since it's a tree, there's a unique path between of hyperedges between any two sections, which consist of subsets of cliques. Okay. Any questions? Okay, because of the topical changer, this is a good time to take a break. So I'm going to pause. We'll take a break now, and then hopefully we will make our way through inference on junction trees for the next part of the lecture. We're now at the point where we have essentially all of the graph theoretic tools necessary to sort of come back to where we started from back at lecture 1 and lecture 2, which is doing inference on trees. Now, even in those lectures, I believe I said all roads lead to trees or something similar. And what we needed to do in order to show that was to essentially show that how one turns an arbitrary graph into a tree. And as you're going to see, we're going to define essentially a set of message passing steps that are very similar to the message passing steps that we did on just one trees. But we still haven't, we just need a little bit of extra machinery, and then we'll essentially be done. And you can think of it as what we've done is, I like to think of it as sort of, we've taken a journey where we started at trees, and we've talked about elimination, and we started moving a little bit more to elimination and this message passing and things, and then we started talking about elimination and non-tree graphs. And then we started going on this sort of purely graph theoretic route that talked about all these different properties of graphs, like triangulated graphs and decomposable graphs and perfect elimination graphs and induced subtree graphs and intersection graphs. And sort of now we're sort of back here, and I sort of think of it as like we're getting back to where we started from in the sense of trees. So if you can think of it, the set of lectures, the past 8 lectures, as this cycle that's obviously chorded, since this is exact inference, then this is what we're doing. So what we're going to do, we're going to define an inference procedure on junction trees that is very similar and analogous to the inference procedure that we defined on just regular trees. The idea is that we're given some probability distribution which lies within the family of some triangulated graph. That graph might be naturally triangulated, meaning that we might have just been lucky and started with a naturally triangulated graph, for example, the hidden Markov model. Or it could be the case that the graph was not naturally triangulated. It was perhaps a 4-cycle or a grid graph that's used in computer vision, and we had to essentially come up with some triangulation procedure to find a triangulated cover of the graph. But in any event, we know that we've got this triangulated graph, and we're doing inference in the family corresponding to the triangulated cover of the original graph, or the original graph if the original graph is in fact triangulated already. So we're going to let G be the original graph with its cliques. So script C of G are the cliques of the original graph. And script C of G prime are the cliques of the triangulated cover of that graph. Okay? And by the factorization property, we know that because we have a probability distribution which is in the family of the original graph, that we can write the probability distribution in this fashion. It's a product of factors. That's just the factorization property. Right? So this is a valid expression of P of x. Now, since it's a triangulated cover, G prime is a triangulated cover of G, we know that every clique in the original graph has at least one clique C prime in the triangulated graph that contains it. So therefore, what that means is that every factor psi sub c of x sub c corresponding to a clique in the original graph can be sort of absorbed into a factor that is meant to represent a larger clique in the triangulated graph, C prime. And so what we're going to do is the following. So we've got a junction tree of Maxcliques. Let's just say it's Maxcliques for now. And we're going to allocate storage in the form of a probability table of some sort for all Maxclique potentials for all C prime, for all of the Maxcliques. Or in other words, for all nodes in the junction tree. For all of, remember, it's junction tree nodes. So it's very much like we've got these nodes, except that the nodes, remember, are these multivariate nodes corresponding to all of the variables within the cluster corresponding to that node in the junction tree. Now, the other thing we're going to do for this particular style of message passing that we're defining in the junction tree is define storage for all of the separators in the junction tree. So remember, the separator is something that corresponds to the edges in the junction tree, and the edges are labeled by the intersection of the two incident clusters. So those are going to be the things that we do. And so we need to know how to initialize all of this stuff, including the separators. So how are we going to do this? So how do we initialize the Maxclique factors? Well, let's start out by just assigning this to be 1. So basically, what does this mean? So this basically says that we, for all values of x sub c prime, phi sub c prime of x sub c prime is equal to 1. Okay? Okay, so that doesn't do very much. The next thing we're going to do is for every clique in the original graph, we're going to find one and only one C prime, sort of the covering clique in the triangulated graph. So this basically means it's covered. So C is a subset of or equal to C prime. And we're going to update this potential as follows. So we're going to say the new potential is equal to the old one multiplied by this. So what does this mean? Let me just zoom in to make sure that this is clear. So this update, this is a table, right? And so what we mean by this is that every single possible value of x sub c is going to be updated in this fashion. So, and remember, because c is a subset of c prime, right? So if we've instantiated values for all of x sub c prime, we necessarily have instantiated all the values for x sub c. Okay? Tell me now if this is not clear. This is like table multiplication. Think of it as this way. So here's a simple two-dimensional example. Let's say you've got a two-dimensional table x1 and x2, and another one-dimensional table of x1. Right? So this one is indexed by, this one here is indexed by x1 and x2, whereas this one here, let's move it down a little bit. This one here is indexed by just x1. Okay? So if we were to multiply, and so on the left we've got a function which is psi of 1, 2, x of 1, 2. On the right we've got a function which is psi of 1 of x of 1. And so when we multiply these together, we have psi of 1, 2, x1, x2 multiplied by psi of 1, x1. That can give us a new table, psi prime of 1, 2, x1, and x2. And this thing should be is perfectly well defined. It just basically means that when we plug in a particular set of values for x1 and x2, we index this table with x1 and x2 and index this table with x1. So it's a form of table multiplication. Okay? And so when we ever see, whenever we see anything like this, that's what we're doing. Now the other important thing about this is that we only do this once. So in other words, we only, for every cluster C, we only multiply it into the table for C prime for one C prime. Because if we did it more than once, we would essentially be overcounting. And so what we end up getting is a representation, a valid representation of the probability distribution in terms of the Maxcliques of the triangulated cover graph. Right? Because every factor is only counted once. Every factor has found a home. It could be the case that there are some Maxcliques that are still 1, right? I mean, maybe, like, let's say there's a max, that's a possibility, depending on what the original graph is and whatever the triangulation is. Right? We're not necessarily saying it's a minimal triangulation. We're not saying anything about the triangulation except that it's a triangulation. Okay? Question?
Okay, if we're initializing the system, that means we don't actually have phi c, right? Or do we have?
No, we do have phi c. So remember, we've got all these potential functions here. We've got it in this form. But what we don't have are the marginal probability distributions. We don't have that for every clique in the original graph, we have it being that it's truly the probability of x1, x2. Namely, it's normalized. It's normalized, like it's a normalized probability distribution just over that subset of variables corresponding to that clique in the original graph. Well, we have the global distribution, p of x. So p of x we know, but that's not. We can't like sum over p of x for every one of these things. We're trying to do. We need these clique potential functions. We need these clique marginals. And the marginals means it's a marginal of the probability. In case it's not clear, what we want is for all c in the cliques of the graph G, we want p of x c. And what is that equal to? That's equal to the sum over v except for x v except for c of p of x. So this is the thing down here. Hopefully you can see it on screen. This is the thing down here that we need.
And that xc is for the max clique and not the smaller clique.
That's for the original graph cliques. Now we talked about once before that if we've got it for the max cliques in cost exponential in the size of the max cliques, we can do a further projection down to the cliques. Right? The cost of the max clique, the cost in terms of exponential in the max cliques is inevitable, and we do a further projection down to the cliques.
Yes,
Okay?
yes, but to get those function values for the max cliques, we are using function values for these smaller cliques, right? In the initialization step.
Yes.
Multiplying one with something.
The original graph cliques, yes.
The other graph. So we have the
And we're just taking these we have these original guys, and we're just coming up with an initialization for the max cliques potentials in terms of these original graph potentials, original graph clique potentials. And so what we end up getting is that we now have a representation of the probability distribution in terms of max clique potentials, where the max cliques are the max cliques of the triangulated graph cover of the original graph. We know we can get the max cliques of the triangulated cover. Right? We can get max cliques of a triangulated graph. We can't get max cliques of the original graph. But we can use maximum cardinality search. We can run the elimination. Once we've got a triangulated graph, we can run find easily a perfect elimination order. We have all these strategies that we can use to find the max cliques. So these are quite doable prospects. And I might say that you use this every day, pretty much, right now. I mean, this is exactly what's happening. So the other thing we do is we initialize the separators just to be identically equal to 1. This is for all s and for all x of s. Yep. Question?
So what happened to the normalization factors?
So remember, let's say it's a Markov random field and there's a 1 over z. So we talked very early on in the class that we could stick, z is just a constant, right? We can just sort of stick z inside of one of the factors. Right? Z is just a constant.
But I mean, there is some way that you have to actually compute it, right? Like, so how would you have computed it?
You actually, it turns out, don't need to compute it. Because what one is doing is essentially summing out everything, and then what one can do is sort of do a local normalization.
But the way we initialize the products here, that will not be normalized. Even if we keep normalizing it, and when we have this clique potential for this max clique, that won't be normalized, even if individual factors are normalized. So
yeah. So I mean, it really sort of depends on how we're using it. But imagine it's the case that we're just trying to construct these marginals, right? So we've got a Markov random field. Let's say it's a hidden Markov model, and we haven't computed 1 over z. By doing this inference, what we're going to do is essentially be computing z. And so then the z is essentially obtainable easily from every one of the resulting factors.
But I guess it's not required as for inference, right? Like it may be required only for learning.
Yeah, for when you're doing actual various forms of learning, then it's tricky to compute Z. Yeah.
I mean, but for inference it may not really be required. So
well, for inference, I mean, oftentimes you can just get it just by doing the normalization. Okay. So.
I mean, like if we are computing marginals for a particular variable, if we end up summing that out also, that will end up giving us the partition marginals.
Yep.
The unnormalized marginals for a variable.
Yeah, I mean, it is like you'll see we can actually get these things. I mean, so Z essentially is sort of implicitly computed.
Okay.
So, but sometimes Z can be hard to get. I mean, because again, this is still exact inference, and if it's the case, as we're going to see starting next week, that if clique sizes are big, then we're going to have to do something tricky. Z is in general a problem, but we're still doing exact inference. Right. Okay. So once we've done this, what we do is we have a representation of the probability distribution in this form, in equation 8.4. Right? So the numerator consists of a product of Maxclique potentials, and the denominator consists of a product of separator potentials. And the separator potentials are used the shattering coefficient minus one number of times in the denominator. Yep.
How do you get the VLSs now?
We're just setting them all to be equal to 1. We're just initializing them. Think of this as a table. This is just a table as a data structure. This is the beginning step. This is the initialization.
I thought when you said this is done.
When we do this initialization, when all of this stuff is done, all of the initialization is done, we have a representation. Now the denominator is just equal to 1, right? The numerator is just equal to the product of the Maxclique potentials, which was initialized to the product of original Graphical potentials. So therefore, we haven't really changed anything. We've just sort of shifted representation around and done a bunch of extra multiplies and divides by 1. Okay. So this might not seem like anything useful yet, but on the other hand, remember that if the graph is triangulated, we know that it's possible to represent the probability distribution in almost exactly the same form, but where the numerator are actual true marginals that we want, and the denominator are actual true marginals that we want. The numerators are marginals over Maxcliques, the denominators are marginals over separators. So we have this representation down here. Whoops, what's going on here? We have this representation down here, and this representation down here. Does anyone see that they're somewhat similar? That maybe it's possible that if we initialize, you remember, each one of these Maxclique potential functions and these separator potential functions, think of them as data structures, or as tables, or just as mathematical constructs. And what we want to do is change them in a way. And first of all, it's a valid representation of the probability distribution. We want to change them in a way such that we get a representation of this form. Yeah, I've already said this. So we already talked about this as well, but this is just a reminder. So we can easily, once we've got the marginals, we can easily compute any original graph clique. Our goal is to efficiently go from the representation in equation 8.5 to the representation, no, hold on, that's not right. We want to go from the representation in 8.6 to the representation in 8.5. So we want to start in 8.6 and end up in 8.5. Yep.
Is there additional requirement for separator to be minimal?
Well, so remember, we're constructing a junction tree, right? It's a junction tree of cliques or junction tree of Maxcliques. If it's the case that it's a junction tree of Maxcliques, then it will be the case that the separators are minimal. If it's the case that it's a junction tree of cliques, the separators themselves might be Maxcliques, as we saw. So all that we're really saying right now is that we've got a triangulated graph and a junction tree. Okay, we're not necessarily putting any requirement, although sometimes I do say Maxcliques. I mean, computationally, if all you're interested in is the cheapest thing, there's no reason to use anything other than Maxcliques. But as I said before, sometimes it's useful because you want a particular marginal, and you have an engine that can produce marginals very efficiently, and so you can sort of hang a clique off of a Maxclique in order to get that marginal over that clique.
I was just thinking, just for that formulation point of view, it's not requirement to make the S to be minimal.
Yeah, and it depends on whether or not you've got a junction tree of cliques or Maxcliques. It's not a requirement. So the question is, can we then go from 8.6 to 8.5 using a message passing scheme very similar? So what we end up wanting to do is we want to essentially make these first of all, these guys are equal, but we wanted to make it such that the Maxclique potential function is equal to the marginal over the Maxclique, and the separator potential function is equal to the marginal over the separator. I mean, I guess based on what I just said, I should just say this is a clique potential and this is a Maxclique, this is a separator potential, assuming it's a junction tree. So we're going to do this using a junction tree, which we know to exist over, and it's easy to get for the Maxcliques of G prime, which is triangulated. So we form a junction tree, and we know how to do that. And we want the clique and the separator functions to equal marginals. Okay. Okay, now this next point is probably, believe it or not, one of the most important points of this class that we're going to see. So if you haven't paid attention at all, this is the thing to pay attention to. Because this is also going to be the basis for all of the approximate inference stuff that we're going to be talking about at the next part of class, like, for example, the marginal polytope and all these other things, which we're going to be dealing with. So the question is, if we want these tables to be equal to the marginals, what is a necessary condition for them to be marginals? Not necessarily a sufficient condition, but a necessary condition. The necessary condition, and this is the critical point, is that they must at least agree with what they have in common. So if you've got one table here and one table here, and they share some variables, and if these guys are marginals, I mean, at the very least, what they have to have is that if you further marginalize down onto the common variables, namely the intersection, they have to agree, right? Because any marginals would do that. So if we take any assignment to variables which don't agree, they're guaranteed not to be marginals. And so what do we mean by this? Let's make this mathematically precise. Let's consider a pair of neighboring cliques in a junction tree. Let's say we've got a Maxclique C prime and a neighboring Maxclique C prime 1 and C prime 2. We've got a separator between them. So if they are marginals, at the very least, we need to have this equation hold. And this basically means that they agree on what they have in common. So remember, what they have in common is S. So we sum out everything except for S here, and we sum out everything except for S here. And what's left for all values of x sub s must be the same, if they are marginals. So it's like a form of consistency. It's a form of local consistency, or local marginal agreement. So anybody have any questions on this? Yeah.
So could they be equal and not be the marginals then?
They could be equal and not be the marginals. But if they're marginals, they must be equal. So I'm saying that it's a necessary condition for them to be marginals, not a sufficient condition.
This seems like you're saying that what they have not in common must be equal, because you're removing what's common.
No, I'm removing what's not common. It's C prime except for S. What's left over is S. So I'm summing out C prime except for S. I'm not summing out S. So summing out means removing. So I'm removing what's not common. It's double negative. If this was an English class, they would correct me right now. But this is not an English class, so we can use double negatives mathematically. So much marginal agreement. Oh, sorry. Now I'm sitting here reading this. All right. I already said this. So this idea, the marginal agreement, is really an important idea. So this is an important thing to recall this moment in your life when if this is the case, the first time you've encountered this concept, because this concept is at the heart of many, many approximate inference procedures as well. So this is a necessary condition. Like I said, it's necessary, not sufficient, for the clique separator functions to be marginals, because it's the case that if they were really marginals, we would definitely have this middle part, right? If they were really marginals, then marginals always agree on what they have in common, true marginals. Okay, let's define a little bit of notation. we're going to use this notation a lot over the next couple of slides. We've got a Maxclique U on the left, which is here, and a Maxclique, or let's just say it's a cluster. Let's not even say it's a Maxclique. Just say it's a cluster. W on the, so U is on the left and W is on the right, and a separator, which is the common part in the middle. And we start out with potential functions, psi sub U, psi sub S, and psi sub W, in a sort of small junction tree or small cluster tree. We're also going to define a commonly used shorthand notation. This is something that tricks people up often when they first see it. But we're going to then therefore spend a bit of time talking about what this notation means because it's useful. It basically represents a new potential over a separator S obtained by marginalizing away from U that which is not in S. So here's what we really mean by this. When we use this notation here, what we really are meaning is that we're summing out x indexed by U except for S of this potential psi sub U of x sub U. So this notation here means that it's defined to mean that, which then, this is really a function of x of U except for S and x of S, right? Because U is equal to U except for S and S because S is a subset of U. And then that's just defined up here to be, so this thing here is defined to be this. Okay, any questions? So remember, it's just table multiplication. And here's a little bit more table multiplication, but we can also do table division. So this notation, which again might seem a little bit weird at first, but what we really mean is that for all possible values of the random variables associated with each of these tables, we're multiplying the table entries corresponding to that. So it's not really matrix multiplication, it's table multiplication. So let's just define W sub S to be W except for S for shorthand notation. So that means that W is equal to S union W sub S by definition. And again, S is a subset of W. And so psi sub W really is equal to psi sub W of x sub W. It's just the shorthand, which is equal to psi sub W. And then here we've partitioned the variables into x sub S and x sub W except for S, or x sub WS. And then also, of course, phi sub S is equal to phi sub S of x sub S. So then this table, this is another table, which is also just a function of x sub S, x sub W. And then x sub W can be partitioned into x sub S and x sub W sub S. And this is just, again, the definition of phi star sub S. So then what this whole thing means here, which is this up here, which we said is equal to this, which is the same as that, is expanding that out to be showing the random variables that it's a function of, x of S and x of W sub S. But then here's the actual multiplication that we're doing. We're basically multiplying by x of S, multiplying by phi star x of S, dividing by phi of x of S, and then multiplying by psi W x of S and x of W sub S. And so that essentially is what this thing means, which is this. Okay, so it's important to know. So, and remember, we're doing this for all values. This is true for all x sub W in the domain. Okay, everybody happy with the notation? Because now we're going to start using it. Now, let's suppose it's the case, remember we said that consistency, marginal consistency, is a necessary condition for them to be marginals. Right? Or consistency is a necessary condition for marginals. Let's say that they start out as being non-consistent. Okay? So if they're not consistent, they're definitely not marginals. Right? So that basically means when it's not consistent, it means that this is true. And we initialized phi sub S to be equal to 1. So we started out by these tables. Remember, we initialized these Maxclique tables as we described earlier. And we initialized the separator table by setting it to 1. And we end up a configuration where, in this little baby junction tree with 2 nodes, things are not consistent. But note that we still have the joint distribution being true. Namely, this is the joint distribution here. It's psi sub u, psi sub w divided by psi sub s. That's still a valid representation of the joint distribution. And also, I mean, one should also remember that there might be evidence involved in this as well. So we haven't talked a lot about evidence in lecture, but basically we can think of, again, as I said once or twice in this class, you can think of evidence as additional sort of delta functions that are multiplied into the potentials associated with the evidence, that basically insist upon those evidence variables being equal to the value of the evidence, and giving essentially a multiplicative factor of 0 for anything except for the values of that evidence. So we can actually, for free, essentially deal with evidence. For free means this doesn't change the computational complexity at all. So we're really talking about orders of computational complexity, big O notation. So what we're going to do then is we're going to exchange information between the cliques via the separators, and in doing so, achieve consistency. And strangely enough, this consistency of the consistency of these clique potential functions and the fact that we started out with a joint distribution is going to be enough to ensure that what we're left with is marginals at the junction tree clusters. So, and we're not, in some sense, we're going to strive for something weaker than marginals, but we're going to get marginals, which is nice. So the first thing that we're going to do is marginalize out the potential at U to get this new separator potential as phi sub s. And this expression, 8.16, can be seen as a message here being sent from the cluster U to the separator S. Sort of like a partial message. It's like a halfway between U and W. The next thing we're going to do is we're going to rescale at W. And we're going to do this. We're going to take the original potential at W, divide out by the old separator potential, and multiply in by the new separator potential that we've just computed. And so this also can be seen as another half message. It's a message from the separator to the cluster at W. Now, it turns out that after we've done this, so we've in some sense updated the potential at W, right? From, it used to be psi sub W, and now it's psi sub W star. Now, what has happened to the representation of the joint distribution? First of all, for convenience, we haven't done anything to the potential at U. Remember, so the U is on the left. We've sent messages out of U through S to W on the right. U hasn't changed, but let's give it a new name just for notational simplicity. We're just going to rename this guy, or just give it's really not even renaming, it's just giving psi sub U an alias. This is like an alias. So we're giving psi sub U an alias, and then we're also looking at the updated potential at W and seeing whether or not anything has actually changed. So here's the new representation. Okay, so let's express this. So we said that psi sub U star is an alias for psi sub U. So that accounts for that. And psi sub W, psi star sub W is equal to the original psi sub W multiplied by phi star S and divided by this. And then what we're left with is dividing by this. Okay, so that sort of shows what's corresponding. I hope you like the color scheme. No? So this cancels out, and what are we left with? We're left with the original representation. So we actually haven't changed the representation of the joint distribution. We still have, in this form, using these new potential functions, one of which is an alias and one of which is an actual new potential function. We haven't changed the definition, or sorry, the expression. So therefore, we still have a representation of the joint distribution over the whole set of random variables. But on the other hand, we don't necessarily have consistency. So why don't we have consistency? Well, because it's possible, it's certainly quite possible to have the following situation happen. In equation 18.19, when we go ahead and we sum out, so remember, psi star sub u is just an alias of psi star sub u, so therefore this is the same as that. And that was the thing that gave us this message, phi star sub s. But then if we marginalize out everything except for s from this new potential function on the right, we put in the definition of the new potential function on the right here. So this guy, let's use a different color. This guy is equal to this times this divided by that. And when we're summing out w except for s, this whole bit is a constant. So we can just pull it out of the summation. But because of the fact that, let's zoom in a little bit here. This term here is not necessarily equal to this, meaning that those two green things that so this corresponds to this, and this corresponds to this. It's not necessarily the case that phi sub s is equal to the sum of the old potential function at w. In fact, we initialized phi sub s equal to 1, so it would be almost extraordinarily strange for this to be the case, that this expression would be an equality. And that would be the thing that would be necessary in order for us to have actually achieved true marginals, or at least this necessary condition for true marginals, namely we've got consistency. So we don't have consistency necessarily, but we do have some progress because now we've gotten one marginal. We've got a marginal, in fact, at w. The new potential function, phi star sub w, is a marginal. And why is it the case? Well, first of all, it's because we started with the joint distribution, which is the product of the cluster potentials in the numerator divided by the separator potential. And so let's look at what this guy is, what this new potential function at w is. So here's its definition. Okay. Phi sub s is just 1, so we don't have to worry about it. Let's pull out this here, and we're left with the definition of phi sub s star, which is this part over here. Okay. Now, why is this next equality true? Anybody see it? The reason why is because, let's just zoom in, we can just put this guy inside the sum, and so we've got this representation up here. And so what we're doing is really just summing out all x except for s. And then here's the joint distribution. And so what we're doing is we're summing out everything u except for s, and what we're left with is the marginal at w, as desired. So we've got the marginal that we want. Question?
Yeah, so if you're summing over u without s, then why are you not left with s?
This is the double negative thing. So remember, we're summing out u except for s.
Yeah.
So what we're left with is anything. So we've got. Let me write it this way. Okay, I will write it down in some detail here. So we're summing out x sub u except for s, and we've got this function here. Let's just call it g. And we've got it's x of u except for s, right? X of s and x of w except for s. When we sum out this stuff, we're left with a potential function which is just going to be some g bar of x of s and x of w except for s. It's a little bit tricky to see this, but I mean it's just the notation. It's sort of this almost double negative-like notation. We're left with a function which is only that which remains, because all of this stuff here, this is the thing that we've marginalized out. Right? We're summing over all possible values of x sub u except for s. And what's left over? The stuff that we haven't summed out. And that's equal to g bar of x of w.
Just to know, I think the notation of H and E, I think, is confused with the evidence.
Yeah, the evidence, maybe so I have an example of a Bayesian network in a little bit that's going to show you how the evidence works. But basically, what this thing here is, I mean, I'm glad you brought that up because I should expand upon this. This is really p of x sub h and x sub e bar, right? So, which is really equal to, let's put this up here, that's equal to p of x times a delta function of x of e equal to x of e bar. So in other words, it really is still a function of x of e, but whenever you sum over these variables x of e, if you don't agree with this evidence stuff up here, then the delta function is going to kill off that term in the sum. So all you're left with is only the terms in the sum that have the evidence variables equal to the evidence variable values that you've observed. And by the way, that delta function is fully decomposable thanks to the fact that what you're doing is multiplying, when it doesn't work, you're multiplying by 0. So that's equal to p of x times the product of e in e of delta of x of e is equal to x of e bar. Right, that's identical because of the nature of multiplying by 0. Okay, as soon as one of them is off, the whole thing becomes 0. And so you don't need to have this large, this delta function, x of e, this delta function here might not seem to be very decomposable. But because of the 0 factor it is. It's equivalent to this sort of, in some sense, independent-like thing. So therefore, you can stick those zeros anywhere you want. Any of the factors could take one of those delta factors. So what you do is you just put them in the clusters where the corresponding variables live. Is that clear? Does that answer your question? So in some sense, like I said before, evidence is essentially free. It doesn't really change anything. Now in practice, like if you were to go to implement this, you probably wouldn't want to have these additional sums over the zeros. You would probably say, oh, look, there's an evidence. Let's just skip that term. I'm not going to sum over all these guys, which are inconsistent with the evidence that I've observed. So, because you're going to save some time, but it doesn't change the sort of theoretic complexity of the procedure. The complexity is still equal to the size exponential in the size of the largest clique. Okay, so this is a message passing procedure, and you're passing messages between two nodes in a tree, and in particular a cluster tree or a junction tree. Nothing that we've done so far in terms of these messages has required it to be a junction tree. We just said we've got these two nodes, these two clusters, and there's some separator, and we pass these things back and forth, and we're just saying that it does happen that the probability distribution is equal to the product of the two clusters divided by the product of the separator. We're going to ultimately need a junction tree, but for right now, that wasn't actually absolutely critical. Okay, so it's kind of like a two-step message. Okay. So how about this? We're still not done yet. We've got a marginal at W, but we still want to get a marginal at U. So what if we send a message back? So we sort of do the same thing. We start with a new W, sum out everything except for W, and get a new potential at S, which let's call it psi star star sub S, for lack of a better term. These are actually the standard. This is standard notation. So this is still another separator potential. So we now have three separator potentials. We've got phi sub s, which was the original one, phi star sub s, which was the marginalization coming from the left, which was u, and now we have phi star sub s, which is the marginalization coming from the right, which is based on the updated potential at w, psi star sub w. So we do this marginalization going from right to middle, and then we do an analogous update, where what we do is we take psi star sub u. I always have to think about saying psi and phi, but I'm just pausing because I don't want to say phi when I mean psi and vice versa. I obviously failed Greek in high school. So this is, remember, this is identical to psi u sub without the star, right? Because that was an alias. So we take psi star sub u, we multiply it by the new guy, the new marginal that we just computed over S, and divide out by the old one. And we get this new one here. And that's going from right to left.
Shouldn't it be phi s instead of phi s star? Because psi u hasn't been changed, so the separator potential for that would just be once, right?
No, so the denominator here, phi star sub s is not 1, right? Because remember, phi star sub s came from the marginalization of the original psi sub u. So the original separator potential of phi sub s was in fact equal to 1, but that's not what we're doing here. What we're doing, and we're going to justify this intuitively in a minute, is actually we're dividing by the thing that was fed into the update of you know, psi star of w, right? And in some sense, psi star of w has phi star s in it already. And if we didn't divide that out, we'd be double counting, right? And in some sense, also, moreover, we'd be double counting. The reason why is because, well, here's the reason. Because, actually, let me say all this stuff because I've got this really nice figure that I think will explain it, okay? But the point is we have to divide out, otherwise we're double counting, and then we will talk about that in a second. In fact, here's literally a second. So phi star sub s and psi star sub u, in some sense, both contain this updated separator potential, phi star sub s. Right? Phi star sub s originally came from psi of u on the left, but we don't want to feed it back doubly into psi of u. So we divide it out before we update psi star sub u. So that this guy, this updated, doesn't end up double counting this thing. Now again, the new updated expression, we're going to, by the way, we're going to create another alias here. So psi star sub w is going to be alias, just for, again, notational consistency, to be the name psi star sub w. So what are we going to get? Let's look at what this thing equals. Okay. So first of all, we've got phi star sub s, which is there, right? We've got psi star sub w, right? And what was that? That was basically equal to, actually, let's use a different color here. Psi star sub w was equal to the original one, psi sub w, which was multiplied in by the message coming from the left, which was this guy, and divided out by the original guy here. And then lastly, we have this updated guy here on the left, which is this original one, which is multiplied in by the separator potential coming from the right and divided out by this one. So this basically is, that blue thing I just did is whoops, hold on. The blue thing I just did is exactly this message here. Hopefully. So you see that, see the correspondence? Now, when we start canceling stuff out, there's a lot of stuff to cancel out. And what are we left with? Something really nice, namely the thing that we originally started with. So we haven't really changed the expression. So that basically means that this whole thing is still equal to p of x. Good news. Haven't changed the expression of the joint distribution over everything, but we have changed the local potentials, which is sort of the thing that we wanted to do originally, right? We wanted to change these tables to be something different. When we sent the first message from left to right, we got a marginal on the right. Now we sent a message from right to left. Maybe we're lucky and we got a marginal on the left, in which case we're done. So first of all, actually, before we do that, I'm getting ahead of myself. Let's talk about the fact that we've now got consistency. So consistency would mean that this updated potential on the left and the updated potential on the right are such that they agree with what they have in common. So with what they have in common means that on the left we sum out u except for s, and the right we sum out w except for s, and what we're left with is s. So let's start going with this, moving forward. So we're just going to plug in the definition of the new message here, of namely psi star star of u, take out what is not involved in the sum, and we're left with the psi star of u. Take this whole thing here and realize, oh, that's just this thing that we originally did here because of the fact that this is an alias for psi of u, right? That's just the alias. Then realize that this cancels out, and so we're left with this. Oh, but that's actually equal to the definition of the message, the partial message that we sent from the right back to the left, which is phi star star sub s. So therefore, we've got local consistency. Okay, so here's the picture that I think sort of summarizes everything that we just said. And so the idea is the following. So we're again starting with this junction tree, where we've got u on the left and w on the right and some separator. We're initializing the potential functions. So this comes from how we've initialized it, and which might, for example, come from clique potentials of the original graph. This guy's initialized equal to 1, and this might also correspond to clique potentials in the original graph. And we've done this in a way to ensure that psi sub u times psi sub w divided by phi sub s is equal to probability of x, the joint distribution. Okay, so the first thing we do is we do this marginalization to get phi star sub s. And then in order to get this, we multiply in this, divide by this, and multiply in this. And here's the expression that does that. And simultaneously, we just rename and do a copy or an alias to psi star sub u. Okay, so then when we look at this new representation, namely this guy, and this guy, we still have a valid representation of the joint distribution, but we do have a marginal at w. Now, we've got the marginal at w. Then what we do is we go backwards. We say, okay, we're just going to do this marginalization here. It's a different color. We're going to do this marginalization. There's the expression of that marginalization. And then once we've got phi star star sub s, we're going to multiply it by this, divide by this, and multiply by this. And we're going to get this updated form according to this expression at u. And then in the meantime also, this is going to be a copy. And so when we're all said and done with this, we still have this, this, and this being a valid table representation of the joint distribution p of x. And moreover, we have consistency, namely that what this guy says, I don't want to use that color. What this guy says and this guy says agrees with each other, what they have in common. Now, the greatest part of this whole business is that we've got the marginal that we've been after. The reason why we have this marginal is because when we look at the final expression at u, namely psi star star of u, here's its definition. here's the common thing. Here's the numerator expression, which corresponds to this corresponds to this, and this corresponds to that. And then we've further substituted in an expression this for this. We cancel out phi sub s since it's 1, and we write the definition of phi sub s here. And this whole thing ends up being, because all of this stuff here cancels out, the whole thing ends up being this. Right? Now, that, I can't remember if I have the expression for this or not. Yeah, this, let's just write it in this way. So this is equal to the sum for W except for S of psi sub U and psi sub W, which then is equal to the sum over the joint distribution, which therefore basically makes this the valid marginal. Namely, P of xu. So this is great. We've got marginals. And we've got local consistency. Now the question is, does local consistency always guarantee global consistency? So so the other question is, like, so I could do an example with a Bayesian network. Would that be helpful to you? Yeah. Okay. So let's do a Bayesian network. So again, we didn't talk about moralization and everything, but let's just use this Bayesian network here. It's a very simple Markov chain. This Markov chain happens to be equal in family to A, B, C. Okay, it's the same family probability distributions, except that we typically are in a Bayesian network of the, we are sort of in the situation where what we have is conditional locally normalized distributions at each factor. So what we have is, for example, probability of C given B times the probability of B given A times the probability of A. So those are the factors that we've got. Let me write that down. So we have that P of x. P of x is equal to the probability of xc given xb times the probability of xb given given xa times the probability of xa. So these are the three factors that we've got to deal with. And the other thing we're going to do in order to sort of make this a little bit more interesting is say that there's a little bit of evidence. So we're essentially observing that, oh, x sub c happens to be equal to 1. So that's an evidence. And maybe we're interested in computing the probability of A given that probability of x of A given that x sub c is equal to 1, or the probability that x of b is given that x of c is equal to 1. So we would need to have the marginals corresponding to that. So we initialize this table here. We form a junction tree. The junction tree is shown on the right, up here. This stuff, that's the junction tree. And we then initialize the table down here to include factors that it can contain. And so the factors that we choose to put in here, in fact, these are the only ones that we can put in, are probability of x of b given x of a times the probability of x of a, which is equal to the joint over these two variables. So in fact, in some sense, automatically, we've got the marginal at ab right away. But we don't know that, right? We just do this initialization blindly. And because the procedure that we just outlined doesn't know that these local factors, when multiplied together, give us the marginal. The next thing we do is for this potential function here, we multiply it by probability of x of c given x of b, which is the only remaining factor of the original one. But we also have to multiply it by a delta function corresponding to the evidence. So that's clearly not a marginal distribution. But it doesn't matter since we don't know. We don't treat either of them as marginals yet. We also initialize the separator to be equal to 1. Okay, so we do a forward left to right message, which consists of this. We marginalize out this table, and we end up getting this local distribution. And then we do an updated message at BC, which is the right clique here, which, after we do a little bit of algebra, just ends up being x of b and x of c is equal to 1. Okay. I guess it's officially not equal to it, but whenever you use it, let me just put this in quotes. Whenever you use this factor, it acts like that, because essentially any factor, there's a delta in there, any factor that basically is involved in a summation where this x of c is not equal to the value 1, terms in that summation are going to get hit by 0, so they're not going to matter. And then when we do a backwards message from right to left, we compute this updated table. We actually multiply it by the factor, so here we have this same thing. Here we indeed have that this is equal to the joint distribution of x of b and x of c is equal to 1. We update the table with this stuff. And after a little bit of algebra, by the way, there were a couple of typos here where I stopped doing x sub a and I started doing a, so I realized that these are typos. But if you won't mind, I will fix these in later things. But what I mean by probability of b comma c is equal to 1 is really probability of x of b comma x sub c is equal to 1. So what we end up getting then is this joint distribution here, the marginal distribution over AB, with the evidence intact, but it's really only a function of x of a and x of b. So when we're all done with this message passing scheme, we've got this marginal at BC and this marginal at AB, exactly what we wanted. And from that, we can, for example, construct these conditionals, x of b given x of c is equal to 1, or x of AB given c is equal to 1, all purely based on local computations, right? So like computing, say, this here based on this here is very easy, right? It's just locally normalizing it. We don't have to go outside of that potential function anymore to get that conditional. Similarly, computing the blue one here, blue one from here from the blue one there, it's just a local normalization. We don't have to go outside that local table. Question?
Why does the B, the phi AB have an XC in it, the evidence there?
Because the evidence has been propagated to be everywhere. So what we're ending up with everywhere is that we end up having potentials that involve phi sub x of c is going to be equaling to probability of x of c except for evidence and x of e. That's exactly what we need. So the evidence is there. This is the result that we want, the resulting marginals that we want with evidence in the model. So remember, this is not a function of any of the evidence variables. The evidence it's just a constant. So you can't like touch these things for variables that are involved in the evidence. That's not there. So it's really only a function of the residual variables that are not in the evidence, namely C except for E. And that's true for all cliques. And that's also if you are doing machine learning in the context of evidence, which most of us do, since learning is basically changing the model to sort of explain the data in some nice way or be good with respect to the data in some nice way. That's exactly the potential that you need to compute, say, these posteriors. Posteriors are, for example, needed for like discriminative training or all those things. That's what you need. Okay, that's a Bayesian network example. The next thing we're going to do when we come back on Monday is to see what happens when we've got a general treat. Because the problem is if we send messages indiscriminately, we can destroy this nice local consistency that we've achieved. So try to watch this lecture again before Monday. I will try to put it online as soon as possible. Thank you very much, and I will see you Monday.